Something I should note is that many figures which I'll be showing are in our upcoming overview paper. We submitted in January. It should be published pretty soon. And here's just a reference to that if you're going back through the slides. So the way I'm going to structure this talk is the first section, I'm going to talk about kind of the motivation, design, and then performance of the experiment we actually put together. I will then talk a bit about the atmospheric conditions that we encountered, what implications we think that has to do with our science, and then finally I'll talk about the analysis that we've done. All right, so first I want to start, why should we study turbulence? Basically, turbulence impacts the atmospheric structure, the circulation on all scales, from local to global, and from the surface into very high altitudes. And we need to improve this in order to be able to describe weather in numerical prediction models more closely. It's worth noting turbulence can be very hazardous. I mean, extreme weather events can destroy property. But then a key point is that turbulence is perhaps best studied at high altitudes, both because the scales are much larger due to the low density, and also there are very sensitive tracers, which are polar mesospheric clouds, which I will get to in a second. Just a couple examples of turbulence. We've got Kelvin-Helmholtz instability in clouds, 1 to 5 kilometer scale roughly. Another example of Kelvin-Helmholtz instabilities in mesospheric air glow, gravity waves in stratospheric clouds, and then also on another planet, the Jupiter's atmosphere is, of course, very, very turbulent. So PMC and PMC-Turbo stands for polar mesospheric clouds. They're also known as noctilucent clouds. A lot of people still call them NLCs instead of PMCs. We're not always looking at them at night, and we're also comparing satellite, which polar mesospheric clouds is perhaps a more useful term. They form basically due to extremely low temperatures at polar summer latitudes. It's actually I think the coldest naturally occurring temperature on Earth. And this happens basically because gravity waves deposit momentum and energy, which drives winds from the summer pole to the winter pole, and then more air fills that, so that area undergoes adiabatic cooling. It goes down to 130 Kelvin or thereabouts. We care about them because they're extremely thin and bright, and thus very good tracers of gravity wave and instability dynamics. So this experiment was actually motivated by another experiment that was another balloon-borne experiment that flew in the Antarctic summer of 2012 to 2013. It was called EBEX. It actually was studying cosmology. It was looking for B modes in the CMB. However, they had star cameras to find out where they were pointed on the sky. These star cameras happened to see polar mesospheric clouds at very high resolution. This was a serendipitous event, but PMC-Turbo was designed to take advantage of the heritage and basically build an experiment which was actually designed from the get-go to see gravity wave and instability dynamics in polar mesospheric clouds. And this image is an image I actually took. It was just with a basic cell phone camera in northern Alberta. It basically just showing what polar mesospheric clouds look like from the ground. They're the bright clouds. The dark clouds are tropospheric clouds. So the reason why they look like that is because PMCs or NLCs are extremely high altitude, which means that when the sun is below the horizon for an observer on the ground, it can reflect off of PMCs. It would not reflect off of tropospheric clouds. This also explains, this figure also explains why we need a balloon. If you have a ground-based observatory looking at PMCs, you are limited you're limited in the angle that you can look at them. You can never just look straight up at them because if you were to mount an observatory in the poles, it would be daylight all the time and they wouldn't show up. It would be just too bright. Your background sky brightness would overwhelm you. However, with the balloon, you can fly much closer to them, which gives you better resolution. You also can look at them at a smaller off-zenith angle. In fact, our off-zenith angles were limited by our balloon. We couldn't look straight up at the balloon. And this image was put together by a colleague of mine, Christopher Geach. So here's the experiment we actually put together. On the left, basically is the idea of this is where we're flying at about 38 kilometers altitude. We're shooting a LiDAR up to the PMC layer, and we're also looking at a swept field of view in yellow. From our gondola, you can see there's a temperature graph as well, and you see the PMCs are right around the minimum of that temperature. To the right is the experiment we built. I'll go through kind of the parts more carefully over the next couple slides, but you can see there's a couple solar panels which are providing power. There's a rotator which is just below the launch vehicle, which keeps us pointed anti-sun, or keeps our solar panels pointed towards the sun, keeps our instruments pointed anti-sun. Along the rim of the cage are several tubes. Those are pressure vessels housing our optical cameras, as well as our computers, which are used to run all the flight control programs. There's also a LiDAR. It's a little bit hard to see because it's silver, and the background is silver mylar as well. But the half-meter telescope is right in the center there. And then the orange thing sticking out the front is the radiator to keep the LiDAR cool. On the lower part, there's basically a box provided by NASA, which provides our telemetry. That's the SIP. There's also some solar panels to power the SIP, and then at the very bottom is ballast hopper to control our altitude. So this is what's inside one of our pressure vessels. Basically, we had 7 of them. All of them contain a camera and a computer, and 4 spinning disks, each of which have about 8 terabytes. The only difference between them is 4 of them have wide field lenses. They have 50 millimeter lenses, which provide us a 40 by 27 degree field of view, and at best about 8 meters resolution. And then 3 of them provide us something more like 3 meters resolution, and it's 15 by 10 degree field of view. All the cameras are the same. They're 16 megapixel. And then kind of the interesting thing about this is they also contain our flight control software, which basically synchronizes all of the cameras together, and it communicates the whole gondola via the NASA telemetry system to the ground. So we're actually able to control this whole instrument live. I actually SSH'd into it mid-flight. And there's 32 terabytes of storage per vessel. We also flew with a sophisticated LiDAR. We believe this is the first high-power LiDAR to fly on a balloon. It was made by Bjorn Kjellstrand, Natalie Kjellstrand, Marcus Rapp at DLR. I'm not a LiDAR expert, so for a lot of LiDAR questions, I would suggest that you get in contact with them. But it was 5 watts, 532 nanometers, 100 hertz. And you can see there's actually an image of the telescope. During float, you see the Earth in the background, and of course the green dashed line is a cartoon, not the real laser. And then you can see the open pressure vessel to the bottom left, showing a lot of the electronics. And then to the bottom right, you actually see the LiDAR mounted with our pressure vessel cameras, or the cameras in the pressure vessels on the gondola, as well as the LiDAR in a straight-on configuration. So we went to S-Range, and well, first we went to Texas and we tested everything and integrated it. We then went to S-Range and rebuilt the gondola again, since we had to ship it. And we were there for about 2.5 months before we launched. To the left, you can see our away team. We've got left to right, Christopher Geach, Bjorn Kjellstrand, Biff Williams, and myself in front of our gondola. And then on the right side, you see our gondola in the high bay. I'm just trying to give you an idea of what the field work was like for this experiment. So we waited and waited and waited and had 8 launch attempts. I'm sure that some of you have talked with High Wind about that whole process of waiting and waiting and waiting for the right weather conditions. But eventually we launched. And I've got a video of what exactly that was like. So this is the balloon. It is much smaller on the ground than it is at float because, of course, there's lower density at float. There's a couple trucks in the foreground for scale, and there it gets released. So now to the left, we've got a wide field of view. I'm in the neon hat. This video was put together by another grad student, Rodbert. And you can see the balloon slowly comes up to vertical over the payload. And you'll see they have a collar release system. The helium is basically pinched into the top of that balloon, but upon launch they need to release the collar. You'll see it's coming off in a moment here, and then we'll zoom all the way down to the payload, and you kind of get more of a sense of scale on the left. There goes the collar. Now we zoomed all the way down to the payload. There's a couple folks for scale holding onto the payload and making sure it doesn't escape, and the launch vehicle is holding it up, and they basically wait for the balloon to get completely vertical, and then they release, the launch vehicle releases the payload so it is able to float up and away, which you will see momentarily. And there it goes. So it's good there's no audio here because we were all making some very goofy noises of excitement.
Bjorn was yelling.
Yeah. So
they include the audio in the NASA press release.
Yeah, the NASA press release has the audio immortalized, me saying something very goofy. All right, so we launched it, and it flew for just short of 6 days. So the map on the bottom, you can see where we launched from, S-Range, Sweden, far northern Sweden, and we floated over Greenland into Canada, and it terminated just below the Northwest Passage. In general, we were something like 37 to 39 kilometers. We ended up capturing about 6 million images. This filled about half of our storage capacity, so we ended up getting, I think, about 120 terabytes. And about 60% of the images actually have PMCs, which is about 85 hours of data. We're taking images, our cadence varies, but we usually took a burst of 4 images every 2 seconds in general. So we have a lot of images. So our data, here is a full instrument field of view. I've actually filled this in with data from flight. I should note that our images were actually in black and white. I've put false color on this to enhance the contrast. So this is, you can see the 4 wide field of view cameras projected from the payload at about 38 kilometers to the PMC layer at about 83-ish kilometers. So this is undistorted images. You also see the narrow field of view in the black frames. So this gives you a sense of the scale. We have something like 200 kilometer by 100 kilometer section of the PMCs, and then the cyan dot pretty roughly shows the location of the LiDAR beam. Just to parameterize our data a little more, so on the left is, I think this is binned by it's binned by a factor of 4 to increase signal to noise, but this is raw data that has been flat fielded from a wide field of view camera, and then I've blown it up to the right, and this is about a 5 kilometer by 5 kilometer section. We also got good LiDAR data. Basically, the LiDAR just gives us a single vertical slice through the PMC layer over time, and we see a lot of interesting things. This particular section of data is about a 4-hour section. It shows us that there's multiple layers. The layers are rapidly moving up and down, and this is our brightest section. This corresponds to some of interesting times during our that we were captured in our cameras as well. So it's good to be able to cross-reference both data sets with each other. And again, this is Natalie and Bernd Keifler are the LiDAR experts.
So what we are seeing there are the amplitudes of these gravity waves at about 82 kilometers. And if I assume that they are upwards traveling waves, what would be the amplitude at the location of the balloon?
So the LiDAR data can give us temperature perturbations. This specific LiDAR data is just reflection off of the PMCs, so we don't see the gravity waves. I will, in like 2 or 3 slides, show the temperature perturbation data from, I think, 50 kilometers altitude to, yeah, no problem. But that does help my transition to the next. So now I'm going to talk about atmospheric conditions. So this is exactly what you were asking about. This is our temperature perturbation measured by the LiDAR. I believe that a Butterworth filter of 15 kilometers has been applied to this, and you can see, so we're not able to measure all the way down to the gondola altitude of 38 kilometers, but we are able to measure from about 50 kilometers up to 80-ish kilometers. And we can see that we have, large-scale gravity waves at low altitudes, or something like 4 to 12 hour periods, 10 to 15 kilometer wavelength. And then there's kind of a transition zone in the middle, and then we see much, much smaller we see larger temperature perturbation, but smaller wavelength and smaller period gravity waves above about the 65 kilometer or so transition zone. So we can kind of extrapolate that back down to the gondola, but we aren't able to measure those last 12 kilometers between 50 kilometer altitude and 38 kilometer altitude.
Next mission will probably put some better in situ probes and also some down-looking cameras, because some of our cameras we put on just for fun recorded some very interesting cloud patterns down below that might correlate up above. Actually saw a lot more wave instability-like patterns down below than I expected. We're a lot higher than airplanes, so we can see some 100 kilometers in the clouds below. But yeah, next time we'll probably focus on getting more of the full profile.
So, but I think the takeaway here is that we're fairly certain that we see large wavelength gravity waves breaking and becoming intense but smaller wavelength secondary gravity waves. And these are most likely the drivers of dynamics that we observe in the PMC layer. We've also cross-referenced our data with the zonal winds measured at Alomar. So this is basically showing us the diurnal tide and semi-diurnal tide effects. There's a lot going on in this graph, so I'll walk through some of these lines. So the black dashed vertical lines are days in UT. The top graph shows both time in UT and also local time to the balloon. Of course, we started very close to Alomar and we drifted away. So there is some phase difference. The black horizontal line shows the approximate location of the PMC layer. The red dashes in both graphs basically show the times when PMCs disappear in our cameras, not our LiDARs, but our cameras. We don't see the PMCs anymore. And the bottom plot is the reflection off of PMCs measured in the LiDAR. And the conclusion that we're currently drawing here is that semidiurnal tides, when they cause eastward winds and thus downward winds, it warms the PMC layers, the PMCs sublimate, and the PMCs disappear. So this is part of the reason that next time we fly, we hope to go at a more polar altitude so that the semidiurnal tide effects are weaker and we have more coverage of PMCs. We're still pretty happy since we have 85 hours of data, but but always thinking about ways to improve the experiment. We've also looked at tropospheric conditions during flight. Basically, the takeaway is that we see we see a jet stream that is over Iceland, and it decreases during our flight. Yeah, we can see that basically kind of the purple stripe at the on the left plots of constant pressure. It's a little bit less prominent on the right plots, but we basically see the jet stream disappearing. We believe that this strong jet stream that is disappearing is the a likely generator for gravity waves that we eventually break into secondary gravity waves and that we see in the PMC layer. I should also say these are all ECMWF analyses. That, along with orthographic forcing and generation of gravity waves, are the sources we think we see. So we have another ECMWF model. Basically, we're looking at let's go clockwise. We have the mean winds on each of 12-hour separated times during our flight. We have a temperature cut, and then on the bottom we have basically a slice along Greenland from the ECMWF model, and this slice is showing essentially gravity waves from 0 to 50 kilometers. Above 50 kilometers, the ECMWF doesn't measure so well, and so we're unable to directly connect this to our measurements, but the takeaway is that we really see gravity waves in the ECMWF model below 50 kilometers. We measure gravity waves above 50 kilometers using the LiDAR temperature perturbation model, so we're quite sure there are in fact gravity waves that were coming up from Greenland due to this jet stream effect. Gravity wave propagation has a complicated relationship with the mean wind, but the data, the mean wind profiles indicate to us that it's likely that the gravity waves reached the critical region and broke into secondary gravity waves due to the background winds. So we also have cross-compared our own data with the CIPS data from this time. So in this figure, I'm showing basically a CIPS stitched together view. North Pole's in the center, and then the PMC-Turbo is basically around the edge for a latitude. So CIPS is an instrument on the NASA Ames satellite that's been imaging the Northern Hemisphere since 2007. From this, we see several effects. We see, of course, brighter and more consistent PMC coverage at higher latitudes, and then it decreases and becomes more variable at lower latitudes. We also see longitudinal variations, which is most likely the semi-diurnal tide effects modulating the PMCs. And then we see a complicated picture here, but we believe we see relationships. We believe we see gravity waves at wavelengths of 50 kilometers to 500 kilometers. There's also, now this is something that we want to investigate more, but there are voids in the PMCs. For example, in the lower right, kind of just above the yellow, just above where the S-range launch starts, there's a PMC void, which are not well understood, and we hope to learn more about them. So we took this CIPS data, and we cross-referenced it with our own data. So here we have two columns. On the left, we basically have the CIPS slices, and then the location and pointing of our own field of view positioned within those CIPS slices. And then to the right, we have what we actually saw in false color at that time and location. So I believe that A and F correspond, B and G correspond, D and H correspond, and E and I correspond. Figure C, there were no PMCs during that time. In general, we were a bit unlucky. Basically, it happened that the ascending and descending periods of the CIP corresponded with the semi-diurnal tide effects, so we don't have a lot of overlap between PMCs and CIPS. But what we do have is very encouraging. So we see that, for example, images D and I, we look at the large picture, and we see, so that's the fourth image down on the left. We see large-scale gravity waves with large wavelengths, and then we see instabilities from tidal shears in image H. So this suggests that we are seeing some interaction between gravity waves and some sort of tidal effect, which is creating a more turbulent picture. And then the bottommost image E of those 5 left pictures and the bottommost of the right pictures, we basically see very large-scale gravity waves in image E of something like 300 kilometers. Meanwhile, in our own PMC-Turbo images, we see something more like 30 kilometers. So there must be some superposition happening here. So kind of just putting it all together, we see a strong modulation of PMCs based on the semi-diurnal tides. We believe that the sources were tropospheric forces like the jet stream changing, as well as the mountains that we flew over. Those are the sources of our gravity waves. And we also believe that large wavelength gravity waves were basically breaking into secondary gravity waves, and these secondary gravity waves were the generators of the turbulence that we actually measured. So I should get to what we actually measured and some discussion of the dynamics. So this is the section of the presentation that I'm going to show a lot of movies, because that's the best way to display this data. So first I should start off with what we're actually about to look at. Basically, you can see there's camera 4, 5, and 6. Those are, call it 2.5 of our wide field cameras. I've simply taken those images and placed them side by side, and then and then I've sampled the frame, so there's a movie. So these are all wide field cameras, and in this particular instance, this is we're going to be seeing Kelvin-Helmholtz instabilities evolve and interact. So we see Kelvin-Helmholtz billows come down from the top of the field of view, and they are increasingly, the billows, you can see that there's basically wisps, that they're interacting as they advect across our field of view. So maybe I'll play this once and I'll go to the freeze at the point that we're very interested in. And then they become much less energetic and they're fading away. They're becoming much less bright and less energetic. Uh-oh. So you see a couple voids and things to the left of the image. But then in about 1 minute, we see Kelvin-Helmholtz billows advect from the top of the screen. And I'll just point it out. I'll just walk over there and point it out. So we've got a lot of streamers interacting between these billows right here, and we're extremely interested in those. In general, Kelvin-Helmholtz instabilities, there's internal instabilities, and there's secondary Kelvin-Helmholtz instabilities, which are developing on the backs of those instabilities. But we haven't seen as much the interactions between the instabilities, and this is a much more violent, turbulent event. It just dissipates a bunch of energy very quickly. So we haven't only been looking at videos and thinking they look cool. We've also been interfacing with the modelers at GATS. So here is a model of exactly such an effect. So here we have a set of Kelvin-Helmholtz billows to the left, basically interacting with a different number of Kelvin-Helmholtz billows to the right. and you can see it basically just devolves into turbulence. And so let's see. So I can point out a couple features right here. Let's see. Yeah, it's a little bit low resolution, but inside the billow, you can actually see some of the internal to the billow instabilities forming. You also see some secondary Kelvin-Helmholtz billows, let's see, kind of starting to form. Sorry, I really should also describe a little more what we're looking at. What this is a simulation of Kelvin-Helmholtz billows. It's going to be 3D, but basically the regions of higher energy are just brighter. So we're really looking a lot at what we're going to be what we see in the PMC-Turbo data, that regions that higher energy collect more ice particles, and that's brighter. Now, of course, we're not simulating ice particles, but the point is, red is more energy is being dissipated in this turbulent event. So what we have here, though, this is what's really interesting. What we normally would expect the internal dissipation of the Kelvin-Helmholtz billows, and we'd expect the secondary Kelvin-Helmholtz billows. But we see that these two sets of billows are really talking to each other in this crazy knotted thing. And this crazy knotted thing is really violently dispersing the energy. So of course this is a kind of a 2D projection of all this energy being put onto one plane so we can actually see it. But this is kind of a three-dimensional twisted knot shape. You can also see that kind of the way that this is happening is that twist waves are developing within this billow. So I'll play this one more time, and then I will... So it just completely devolves into turbulence at this point, which is what we expect, that it just breaks down. And I would also refer that if you're more interested in this, we should discuss it further, and we should have the modeler who actually made this involved as well. So this is basically this knot, which I pointed out right here, frozen in time, and then we'll just rotate it so we can see exactly all the structure that's involved with this interaction. You can see that the twisting involved in this this interaction, the twist waves are really what form kind of the core of this interaction. So we're still working on this, and we have yet to publish a paper. But this is really the active field of study right now. We also have several other events we're interested in. Of course, it's not just the Kelvin-Helmholtz instability. This one is close to my heart because it's what I'm studying right now. But also, when gravity waves break, they, depending on the background conditions, they tend to form either vortex rings or cusp-like structures. And in this particular event, it's very similar to last event where I have 4 wide-field cameras lined up side by side by side, and we basically see the formation of herringbone structures, which will then break down into vortex rings and then basically break further into a large section of the sky which is covered in what we've kind of just called cusp structures. So I'll go ahead and play this. So there's also a lot of dynamics in this particular video, so it's a little bit overwhelming, but I'll point out what we think are really the interesting features, or especially interesting features. Yeah, so here we've got some herringbone structures forming in camera 5, and then you can see, so these two cameras are overlapping, you can see that they kind of turn into vortex rings right here, and then this entire region of the sky breaks down into cusp structures. You can see all these cups scattered throughout the image. So I can walk through that again, and maybe if you're watching for it, it is clearer the second time. So we see the herringbone, and these herringbones are going to create those vortex rings between camera 4 and 5. And then that entire region, kind of the camera 4 and 5 region, degenerates into the cusp structures. And this is really a telltale sign of a gravity wave that has been breaking. We're interested because we see several different types of results of the gravity wave breaking. We also can see some sort of front that's developing in camera 6 and 7. We're also particularly interested in this because this is not the first time we've actually seen this. We also observed very similar features in the EBEX flight. And so if you see in figure A, the top figure, that's actually just an image from EBEX showing the cusp structures. In image B, that's the result from a numerical simulation of a multi-scale dynamic flow. And it's showing this is what happens when, in that simulation, you create a wave that breaks. So we're also investigating this this herringbone vortex ring and cusp structure. Just to mix things up, I'm gonna show the evolution of a mesospheric bore, which we have captured. So this is a projected movie where the other movies have been basically our wide field camera just stitched together. This is projecting into real coordinates on the sky. And we see a mesospheric bore basically propagating, advecting across the wave. We see that it starts as one phase front, but several other wave phase fronts are induced. If you're wondering what all that flickering is, it's actually an aurora, which we're not at all scientifically interested in, but it's quite cool, I think. And we can see some interactions between the phase fronts as well. So my colleague Christopher Geach is actually the one studying this particular interaction right now. We mounted narrow field cameras onto our gondola, and we did that to get higher, to be able to look at smaller scale features. So, for example, here we have also captured some very clear formation of vortex rings, which we can see advecting through the. Whoops, that's a different. We can see these vortex rings form and advect through the field of view. Again, we're quite sure that a gravity wave breaking is what is creating these dynamics.
You know if there are multiple layers in the LiDAR in that case? Looks like there might have been two different motions.
Yeah, there's certainly multiple layers of PMCs that we see. The LiDAR is in the next narrow field camera over, so we can't directly measure the layers in this image like we can in another narrow field camera that we have. And then this is the final movie that I'll show you, but we see very, very small scale, some of these kind of herringbone features that are propagating into vortex rings in this video. And we're quite interested in this because this is a much smaller scale gravity wave that is clearly breaking in here. We have some reflections down here, but or at the bottom of the field of view. But right in the central part of this field of view, we're really interested in these features, and we're also undergoing efforts to model and try to describe this. So of course, all of this work is being done right now. I mean, we retrieved the data in September. We had to catalog it, and but our ultimate goal is to really describe exactly these effects that are going on using modeling, and then we can quantify what exactly is happening at the atmosphere. So going forward, the Kelvin-Humboldt instability that I've shown you and the gravity wave breaking front, or the mesospheric bore, that I also have showed you, are currently being studied by myself and my fellow grad student, and we're continuing to try to compare them to models. The overview paper has been submitted and should be coming out soon. The instrument paper is also in preparation and should be coming out soon as well. And so we're interested in so we have this about a 24-hour continuous period of PMC coverage, and we're interested in using that to explore how PMCs react to the semidiurnal tidal effects, because in the 24 hours we have several phases of those tides coming by, and then of course we're still trying to compare our own data to data from various other groups, and understand how topography and tropospheric weather are influencing gravity wave dynamics. And then finally, we're also continuing to relate our own imaging with imaging from the CIPS. So, thank you, and let me know if you have questions.
So what is the relation between the brightness you see and some of the atmospheric properties? So it is the intensity of PMCs, but is that, I don't know what kind of timescales you're talking about. Does it reflect the temperature? That is where you see PMCs, it's colder, or the time lag too long, or so what are you saying?
Yeah, so what we're seeing is the intensity of the PMCs, but whether that is, I think there's a lot of things that can cause a more intense PMC reaction. I mean, one is simply winds pushing the ice particles around, but another is the temperature perturbations raising or lowering the temperature of the PMCs, raising or lowering the temperature of the sky, which can cause ice particles to either form or sublimate. There is some question, which is how many. It's difficult to disentangle. When you've had, for example, a structure which is a temperature perturbation structure, which has caused the sublimation or formation of ice particles, and then that whole structure is advecting past our field of view, versus how that is evolving. I mean, clearly we see the structures changing as they move past, but for example, when we're looking at LiDAR data, we're more likely sensitive to structures advecting past us. So I guess it's a little bit complicated.
Yeah, and there's also a cutoff. If the ice particles go above or below a certain size, then you stop getting visible scatter. And so you can get rapid changes in reflectivity, very small temperature changes, but if the particles are a lot bigger, then the change is more gradual. But for most of these simulations, we're treating them more as a non-varying tracer. But for longer time periods, they're definitely going to be changing with the thermodynamics.
Yeah.
So in the 6-day flight, you said you have nearly 24 hours continuous observations. What limited that you couldn't go beyond 24 hours?
No, so that's 24 hours of PMCs that were there for about 24 hours.
Oh,
So after that, they just disappeared, yeah.
Yeah,
they just don't last that long.
Yeah, because of we think because of the semidiurnal tide forcing air eastward and downward and warmer.
and we flew farther south than most missions do. We stayed between 65 and 70, and often they go up above 75 degrees on the flight path.
Yeah, I'm very aware of that.
So going forward, we hope that our next flight will be from Antarctica, and if we launch from McMurdo, we're much closer to the poles, where we get brighter PMCs and better PMC coverage. We launched from the northern hemisphere. Well, we had gathered data already from the EBEX flight from the southern hemisphere, so we were interested from the northern hemisphere, but also as just for practical purposes, NASA didn't have room in their ballooning schedule to fly from Antarctica.
Did you have any accelerometers on the gondola to see whether any motions that the balloon and gondola were subjected to were related to
Let's see. So I think we did have, I believe that Burned included some accelerometers, but they were not sensitive enough to, those are really for termination to see how much, what type of G's we were experiencing on the falling. However, we actually do know quite precisely how much our gondola was moving, because in our data we can actually see stars, which is how we get the pointing and the projection for our images. So actually, we might be able to see. I think this isn't quite high enough resolution for seeing stars, but we.
There's one star in the middle there,
Yeah.
right?
Oh,
See it moving. So we get angular deflections pretty good to the extent that local waves deflect the gondola. We should be able to see that, but I don't know if it's more that or just more up and down, which we may not be as sensitive to. But definitely should put a higher resolution in situ package on the next flight.
yeah, we certainly were worried about motion blur and the. So NASA stabilized us anti-sun, but of course their rotator isn't perfect. Yeah. But we're confident there aren't at least any very large scale swings in our field of view. Yeah. Oh yeah.
So you showed a few events. Are those, is that kind of typical behavior or are those unusual? Do you have a sense of?
So we certainly have a lot of very interesting turbulent events during our flight. It's not always that interesting. I mean, I selected those to be particularly interesting, but we have, just estimating, we have dozens of events that are similarly interesting for our 6-day flight.
On the scales, sizes that you see, were you saying you get down to like 8 meters or? I
Yeah.
don't remember what I was saying.
So here's a good example.
Where you think that falls in inertial subrange versus, are you getting toward the viscous subrange or?
Yeah, so let's see. Oh boy. So I think the inner scale of turbulence, it's definitely less than 8 meters, but I believe it's closer to our 3-meter resolution that we can get with the narrow field cameras. Of course, the 8 meters is right along our most off-zenith, our least off-zenith angle for the wide field cameras. Once we get down towards the bottom of our field of view, because they're projected, they're just projected at a lower angle across the PMCs, we get much worse resolution, maybe 20 meters per pixel. However, our narrow field of view are much smaller, so we typically there's still some variation, but it doesn't leave dramatically from the 3-meter per pixel resolution. Yeah, we don't quite get to the inner scale of turbulence. We're actually my colleague has been investigating that over the last few weeks, and I don't think he has a definite answer just yet.
Actually, Bjorn, I think if you assume relatively aggressive turbulence, that implies an inner scale around 10 or 20 meters at these altitudes. And so the EBEX data, which had 2-meter resolution, was able to actually see structures at the inner scale of turbulence. It's pretty remarkable. Our signal noise was a little higher here than we liked, but still we can see deep into the inertial range in most cases.
There you go.
what are the typical Reynolds numbers in the dynamics in these regions?
The typical Reynolds numbers. To be honest, I think I'm going to refer to Dave for that that question.
Well, the Reynolds numbers depend upon the scales of the events. So in this experiment, we saw vortex rings that varied in diameter from anywhere from as small as maybe a half a kilometer up to 7 or 8 kilometers. I mean, these are huge, huge smoke rings in the sky. And our modeling tells us that the vortex ring diameter, when it's fully formed and just before it breaks down, is a pretty good guide for what the vertical scale is. The vertical scale, the gravity wave, the vertical wavelength is typically 2 or 2.5 times the ring diameter. So an 8-kilometer ring would imply a 20-kilometer vertical wavelength. And that gravity wave would have a very, very large Reynolds number. It would be of order tens of thousands. Smaller scale events would have correspondingly smaller Reynolds numbers and lead to less intense turbulence, I expect.
I'm asking the question because I think that your simulations of this, the gap in actual Reynolds numbers that you can realize in numerical code and reality isn't that big as in turbulence simulations that we do for solar situations. Is that right?
Yes, the nice thing about doing an experiment at these altitudes is that the Reynolds number is orders of magnitude smaller than it is lower in the atmosphere, and so we can actually achieve Reynolds numbers in our simulations that are comparable to what we can measure in these cases.
Yeah, but
Any more questions? I think we did.
Thank you.